Hello, everybody. This week we're going to be talking or starting chapter 15, which is all about active filters. Um, Now, active filters are filters that are made using op amps. Okay, we've been exposed to filters before, but mostly they're passive filters, RC filters, which we'll talk about here momentarily, just as a point of reference as review. But active filters have some definite benefits, which we'll get into. Also, understand that active filter design is a whole field in itself. Matter of fact, there are entire courses, multi-section courses dedicated in some curriculums, like at UCF, for example, that just focus on active filters. And there's quite a bit of math involved, and it's very involved and detailed. We're not, fortunately, not doing that in this for this treatment. It's just one chapter, but just understand it goes way beyond what we're about to talk about. That said, what you're going to hear in the next 2 weeks or 3 weeks is very useful. I think it'll allow you to, when we get done with this, you'll be able to design a low pass or high pass or band pass filter that'll work just great. And the types of filters that we're going to be looking at are the most common filters that you will encounter in your careers or field or whatever it is you're going to be going into. So it's very valuable. It's a good basic foundation for filters. Okay, so most of you or all of you should have had a good bit of exposure to filter um, technology or filter circuits in your AC circuits class, and also quite a bit in the semiconductors class, high pass, low pass in particular. And here's a diagram of some basic filter responses. That's gain versus frequency. So this would be a low pass filter on the left here because it passes low frequency. The second one is high pass. It shows that all frequencies past a certain cutoff frequency here are passed. This is a band pass characteristic. A certain range of frequencies and are passed, and this one is a band stop filter or a notch. If we get into a little more detail on that here. Get my thing to work here. Yeah, so that's what the lineup is there. Some parameters associated with filter response. Again, this should be somewhat of a review, but let's go through it. So this is the pass band. This is the range of frequencies that the filter allows to go through. Okay, and the point at which it begins to stop frequencies is called the cutoff frequency, FC. And that is defined by the point at which the passband gain, okay, this is gain normalized to 1, the passband gain is minus 3 dB. So it's 3 dB below where the passband gain is. And that's actually equivalent to 0.707 or about 70% of the passband gain. So you can, it equates it to linear terms. The transition region is where it's on its way down. In other words, the gain is on its way down. And it's minus 20 dB per decade. You should remember that. It's 20 dB per decade per pole. A pole is a RC combination, as you see here. It's a combination of resistor and a capacitor. And you know this is a low pass filter right here, this circuit. Why? Because the capacitor shorts out high frequencies, right? So as the frequency gets higher and higher, this becomes more of a short circuit. At a really high frequency, this is 0 ohms, this capacitor, or close to it, so you don't get much voltage out here. So you can think of it as a resistor divider. And this capacitor is a frequency-sensitive resistor, or a variable resistor that is sensitive to that is varied by frequency. That's always the case. Okay. So also along here, we're showing frequency is in decades. So here is 0.01 FC, 0.1 FC, FC, and then 10 100 and 1,000 FC. So this is a Bode plot. Perhaps you remember that Bode plot. So it's a logarithmic graph. And the reason we do that is because we're able to show wider frequency ranges in a smaller compressed space on a graph paper. And you can actually get logarithmic paper. I think you can go to graphpaper.com or something like that and print this stuff out. So you don't have to, if you want to do a Bode plot on a graph, for example, for one of your labs, you don't have to go to the bookstore and buy logarithmic paper. You can print it on your printer if you want. Let's see here. So high pass filter, same thing, only totally different, right? Totally opposite. It passes all high frequencies. But on its way down, as you get lower frequencies, you get to a point where you're 3 dB down from the pass band gain here. That is same thing, it's the cutoff frequency. And as you get lower and lower in frequency, the gain becomes less. And in that case, we have switched the positions of the resistor and the capacitor. This capacitor becomes what? A short circuit, just as the other circuit, it becomes a short to high frequency. So that's why you get the pass band. Everything's coming through, right from the voltage source right on out. But as you go lower in frequency, what happens to the capacitor? It becomes an open circuit. You can't pass a D-cell battery through a capacitor. Can't do it, right? So as you get lower and lower frequency, this becomes down towards 0 hertz, right? Or DC. You don't get any signal through. And as we go through these filter circuits, I encourage you to do that if you want to figure out, because this is, for most of us, probably pretty straightforward to see that this is a high pass filter, because you get a capacitor in series, right? Anytime you have a capacitor in series, it's always going to be a high pass situation. Sometimes, as we'll see in some of these circuits, maybe next week, where we have more capacitors in the circuit in different places, it might not be as easy to determine whether it's high pass or low pass. And the way that I like to tell you how to solve these problems is to take all the capacitors and short them all out, replace them with wires. That'll simulate a high frequency signal going through the circuit. And if you still have an output when they're all short, because the circuit becomes very simple, and we'll see this probably next week when I explain some more complicated circuits. If all the capacitors are shorted out with just wires, you take a look at the circuit, it becomes very simple. Either there's a signal out there or there's not. In a similar method, if you take all the capacitors and remove them, in other words, don't put wires in there, just remove them completely, open circuits, that'll simulate a low frequency signal, right, or DC. And if you still have a signal coming out, right, then you know it's a low pass situation. So we'll go over that again, but and I'll emphasize that again because it's a really great way to analyze very quickly whether or not you're looking at a high pass or a low pass circuit. Band pass is a little trickier, but we'll get into that too. Excuse me. Okay, so band pass filter passes all frequencies within a certain range of frequencies. There's two critical frequencies. One is the lower frequency cutoff, and one is the higher frequency cutoff. So we have FC1 and FC2. And perhaps you remember from your AC circuits, you can do an RLC circuit, and at resonance, meaning when the inductive reactance and capacitive reactance are the same, you get this center frequency, F0. On either side, if you go lower in frequency, what happens? Lower in frequency, what happens to these parts, the capacitor and inductor? Well, at a low frequency, the inductor is what? That's a short circuit. It's just wire, right? Whereas high frequency, that coil of wire generates this magnetic field. It doesn't want to let that high frequency through because it has to build up the magnetic field and collapse it. And it won't allow you to do that very quickly. So it becomes an open circuit at high frequency. But what happens to the capacitor at high frequency? It shorts out, right? So over here at high frequency, the capacitor's coming into play and shorting out your signal. Whereas at low frequency, the inductor comes into play and shorts out your signal. But at one magical spot, they're both equal in inductance and inductive reactance and capacitive reactance. In other words, the same impedance. And that's right here in the middle. And the signal can get through. So that's an RLC circuit. It's a band pass filter. Now, if you put that capacitor and inductor combination in series instead of parallel, what you get is a notch filter. All right, it's a point at which the frequencies are the special frequency when the inductive reactance again and capacitive reactance equal, which is called resonance. You get this notch. You get the lowest gain coming through the circuit, the lowest output signal versus input signal. Now, on either side of this, the same stuff happens, right? At low frequencies, what happens? The inductor is a very low impedance. It's a short, I mean, except for the winding resistance. So you get signal. Again, at high frequencies, the capacitor becomes a short. So you get signal going through. So it's all good. But at some point, right, both of these have some inductive or capacitive reactance, and you get less signal. So you get a voltage divider, basically between this load resistor and whatever the impedance is of your parallel network here. And again, you can do that analysis on any circuit that has capacitors or inductors in it, any reactive circuit element. Please don't hesitate to do those boundary conditions. Find out what it's running at, what it looks like at DC. All right, at DC, the capacitor goes away, right? All the inductors, that's all that's there. And at AC, at high frequency, the inductor goes away. It becomes a very high impedance. The capacitor shorts out because capacitors are shorts to high frequencies. So you can study that. I mean, you can use that exercise to figure out what the circuit does. Okay, so those are passive filters. Let's talk about active filters. So we can use op amps, basically put these filters in op amps and optimize their performance. Let me go back a slide or two real quick here. I want to look at this circuit here, this low-pass filter. Great, it's a low-pass filter, single pole low-pass filter, and we use these quite often. It's not something that is not ever used. It's used all the time, very common. However, it's got some drawbacks. What are the drawbacks? Well, you've got this resistor in series with the source feeding the output, right? Well, normally what you want is a very low output impedance from your circuit. I mean, there's only a certain amount of current that this circuit's going to be able to produce at V out. Because as soon as you start pulling more current, what happens? You get voltage drop across this resistor, and your signal, even in the pass band, is going to come down. So this is going to come down if you load this circuit. So that's a problem, right? So if we go over to active filters, if we put an op amp in this, we can take advantage of the low output impedance of an op amp and fix that. And we'll see that in a moment. Now, op amp circuits, as we've learned, have feedback, negative feedback. And these circuits do use negative feedback. Just regular negative feedback, just like we were studying in the first chapter, in chapter 12, okay? However, when you put a filter in the circuit, what happens is that feedback becomes something special. It becomes something more than just the gain. In other words, those two resistors, the RF and R1 or RI, right? Those play a different role, or more role than just gain, okay? They do of course control gain, but they also control something called the damping factor, okay? And the damping factor, depending on how much gain you put in, will determine the filter characteristics of your active filter. Now, remember a minute ago, those low pass and high pass filters, they had a real smooth roll off, right? Right, it was just basically 20 dB per decade. If you put another one and cascade with it, it'll be 40 dB per decade and so on. Of course, now that resistor that was in there, now you've got two of them. So you've really made a difficult situation even worse, because now you have even more impedance in line, more resistance in line with your output signal, which you don't want. You get 40 dB per decade or even 60 if you put three of them, but then your overall gain is going to go way down in the passband. In active filters, you don't have to do that, okay? But you will get different filter responses. For example, there is let's see, I think these do, okay, so the Butterworth filter is like butter. You can remember it that way. It's just nice and smooth, okay? It is a typical 20 dB per decade response that we've been talking about. 20 dB per decade per pole. So if you have two poles, you're going to get 40 dB, and so on. Chebyshev has a much more rapid roll-off. You see how more steep this is? Chebyshev, kind of fun word to say, huh? But the passband has ripples. See the ripples? So as you're going through frequencies, you're going to get a different gain at, let's say, 1 kilohertz than you are at, let's say, 10 kilohertz. Sometimes that's not such a good thing. You want a flat passband like the Butterworth. And the Butterworth has a basically flat passband, whereas the Chebyshev doesn't, right? And then lastly, we see this Bessel filter, which has a much more gradual roll-off. So it's a little lazier than the Butterworth or the Chebyshev. And you think maybe that's not so good, but the Bessel's special in that it's got what's called a linear phase response. And that's important, especially for non-sinusoidal signals. I'll explain that in a moment. But the phase response, in other words, the phase angle between the output and the input, is constant through frequency. So if you have a 90-degree phase relationship, in other words, the output is 90 degrees out of phase with the input. At 1 kilohertz, at 10 kilohertz, the output's going to be 90 degrees out of phase with the input. It stays constant. Does that make sense? So at 100 kilohertz, you still have 90 degrees on the output versus the input. Not so with Butterworth or Chebyshev. You might have 90 degrees at 10 kilohertz and 120 degrees at 100 kilohertz. It changes. And the reason that's important, why Bessel filters are used to keep phase response linear, is for non-sinusoidal signals, and non-sinusoidal signals that are not sine waves. For example, square waves. Square waves are made up of an infinite number of odd harmonically related sine waves. So 1 kilohertz, 3 kilohertz, 5 kilohertz, so on. It's a Fourier transform. All of those frequencies have to have the same phase if you're going to filter it, okay? And then retain that square wave at the output. And a Bessel filter is used to filter non-sinusoidal waveforms like square waves and so on. So it's used in radar systems, for example, that are pulsed to keep the, and phase is king in radar, right? Everything is about the phase. That's how weather radars work. That's how all kinds of different radars work, using the phase response of what's coming back. Okay, let's talk more about the damping factor. Damping factor will determine whether you have a Butterworth, Chebyshev, or Bessel response, or any other number of responses, which there are others. Again, a pole is a mathematical definition of a single RC filter pair. All right, so single pole is 1 RC, and we'll see that, which as we saw before, but we'll see that again. It says here non-redundant reactive elements. Well, that means one capacitor, but not two capacitors in parallel would be redundant because they form one. But if they're in series, that's not that. Depending on how they're connected, that may not be redundant. Okay. So you're never going to have to determine mathematically the damping factor for a particular filter characteristic, because those are given to you in tables. They're Bessel tables, okay? Bessel function tables, which are really a mathematical monster, which we don't deal with here. We don't need to. But the order of the filter is, well, the Butterworth response is determined by the damping factor and the order of the filter. So, for example, if you have a second order filter, need a second order filter, that means 40 dB per decade, right? You're gonna have two capacitors in that circuit. We'll see that in a moment. We have two poles. The damping factor is going to be 1.414, and that is a gain resistor pair of 0.586. Now, this, as we'll see, this is a non-inverting circuit, so the actual gain is 1.586, right? Because it's 1 plus R1 over R2, and we'll look at that here. Yeah, 1.586. So let's take a look at the circuit. Here's the circuit. We have two capacitors in this circuit. This is, we're going to do this as a Butterworth filter. And FC desired is going to be 1.5 kilohertz. And this is a basic two-pole low-pass filter. Notice the negative feedback here. It's what we've seen before. If you take away all this stuff, these capacitors and resistors, and just replace this with a wire, what have you got? You have a non-inverting op-amp circuit, and that's what this is, okay? Except we put these capacitors in here and resistors to make it a filter, all right? So, is this a high-pass filter or a low-pass filter? Now, it says it's a low-pass filter, but let's take a look. What happens at high frequencies? Well, immediately this capacitor shorts out. So your signal input to the non-inverting input goes away. So immediately you know it's at least a low-pass filter. All right? In a similar vein, this capacitor shorts out, all right, which further reinforces this capacitor in bringing the signal down. All right? So let's take a look at some numbers here. So if we choose R and C, again, you're going to put this on your equation sheet, but boy, I tell you what, you might want to just memorize this one because it keeps coming up over and over and over again. You've seen it before. 1 over 2 pi RC, it just rolls off the tongue. 1 over 2 pi RC is always the cutoff frequency for this circuit and for the high pass and for several other circuits we see from here on out. And this was the same in semiconductors, and I'm sure it was the same in your AC circuits. So if we want this 1.5 kilohertz, you can choose, and they choose a random resistor, 22K. This is a nice range, 22K. You don't want to choose something too high or too low. 22 is pretty nice. You could choose 50K. You could probably get by with 10K. Don't go to 100K. Why? Because you get too high a value here, the currents start dropping down, and then you start competing with noise. All right? You have to keep the current strong enough to stay above the noise. If you get too low, however, you know, like 22 ohms, then you're going to end up drawing too much current. So 22K is usually pretty good. In the 20s, tens of Ks, you're good. When you solve this equation, put 22K in here and solve and put 1.5 kilohertz here, solve for C, you get 4.8 nanofarad. All right, now there's a standard value of 4.7 nanofarad, which they choose. And so we get 22K. Yeah, you set all the capacitors and all the resistors equal. In other words, the two capacitors are both 4.7 nanofarad. The two resistors are 22K. Okay. And I think, let's see, yeah. So I'm going to do the two-pole next week. we do this again for a 2-pole. So I'm sorry, we're going to do the, for a 4-pole, we're going to do the 4-pole next week. So, yeah, okay, so what's the damping factor for this one? What do we need? We need 0.586. So R1 over R2 is 0.586. So to get that, we choose R1 at 33K, and then we solve for R2, ends up being 56K. And you can go, if you want to do a voltage divider or gain equation, solve it quickly, you can actually go on Google and type in op-amp gain equation, and there's calculators, online calculators to help you do that. But again, you should have this on your equation sheet because you may not have time to do that for a midterm, okay? So the next slide, I think, is what I was getting at. Okay, so the 2-pole Butterworth design. Here is our 33K and our 56K, and this is the complete design that we have with your 22Ks, your 4.7 nanofarads, and your damping factor resistors here. So this is going to be a Butterworth filter, and you can put it in multisim. And here's that nice gradual, like Butterworth response. It is a flat pass band, okay? And you can measure this at, and this should be 40 dB per decade, right? All right, 40 dB per decade. Yeah. And I think, yeah, 40, yeah, for critical frequency, mid-band gain is about 4 dB. And we have multi-sim at 1.547 because we chose 4.7 instead of 4.8 as the calculator was. And I think what we want to do here, 4-pole, so we can do a 4-pole low pass. What do? Well, you cascade the two poles, okay? Just put them right into each other. And we're going to get into this next week because we're kind of getting on time here, but notice this output comes right off the op-amp. And this output off the first stage did too. Let's go back to that real quick. See, for just 2-pole, comes right. So you're getting all of the advantages of the low output impedance of this op-amp. So you can drive some current out of here, okay? Whereas the passive design, you couldn't do that because that has a resistor in series. This does not. So you're using the full advantage of the op-amp here, full of its output impedance. Additionally, you have the input impedance of the op-amp that is high, although you probably have something in the 40 or 50K region because of these two resistors here. But that's okay, that's real high, okay? All right, so next week we're gonna go on to do other filters. We're gonna do a high pass filter and perhaps look at some others. So if you have any questions, please post them into the discussion. I also want to say one more thing. I'm very impressed with your labs. They look really, really clean and for the most part, very complete. So keep up that good work. I hope you're able to get enough out of the multi-sim simulations. I know it's not as good as the hands-on lab, but we're still doing the best we can. I think we're gonna have to stay this way through summer. Fall, they're telling me we're gonna get back to face-to-face. So cross our fingers. In the meantime, stay healthy, everyone. Thank you.